Hi, welcome to SignalPath. I have a really special episode for you guys today. I have the privilege of introducing you to the Keysight UXR series real-time oscilloscope. This oscilloscope isn't just a little bit better than the state-of-the-art, it's a giant leap forward. It can do 256 gigasample per second with 110 gigahertz of analog bandwidth on 4 channels simultaneously. And it does that with a 10-bit resolution A to D converter. And it doesn't matter how many channels you have active because it does 256 gig sampling all the channels at the same time. This means that it captures, processes, displays, and stores over 10 terabit per second of information in just this one box. It's just unbelievable. In order to get to this kind of specification, they've had to innovate at every layer of the design, and everything had to be custom made from scratch, from the front end connector to the preamplifier to the samplers to the A to D converters, and even to the IC that interfaces the memory to the A to D converter had to be completely custom made in order to accommodate this massive amount of data that's being captured. They also had to create their own calibrator module with NIST calibration certificate, which they can ship to you, and you can calibrate your scope directly in the lab. There's really nothing else like this, and the fact that they have gone to this point is really amazing. If I told you a couple of years ago these numbers, you would have never believed it. Now, this 10-bit A to D converter, which is sitting at the heart of this scope, is the same one that's in the S-series scope, which I did a full teardown and review, and that's been refined and upgraded to be put in here. Now, not only are we going to take a look at it and see how it behaves, I'm going to take it apart. Well, not quite take it apart, but they've really sent me the acquisition board and they've sent me the front-end sampling modules. And I'm going to take all of that apart, look at it under the microscope, and really give you a detailed view of how it works, what kind of engineering has gone into it. I'm going to take a look at how they've accomplished this massive amount of bandwidth. It's actually 113 gigahertz, which is extraordinary. There's so much you can do with this. It opens up test and measurement capability for optical coherent communication and even wireless communication if you want to capture many wireless channels at the same time like nothing else before. So I'm really eager to take a look at it. It's going to be a long video broken into a few sections. You can look at the description to jump to the section you want. This is still a prototype, so for really detailed testing we're going to have to wait a little bit longer, but I still do a couple of experiments with it, which I think shows you how amazing it is and what it can be done with it. So without any waiting, let's go check it out. So before we look at the architecture of the new oscilloscope, I think it's worthwhile to appreciate how people have been doing this kind of high frequency sampling in the past, or at least up to this point. Now, Tektronix, LaCroix, and Keysight all have employed various techniques to overcome the limitations of time-interleaved A to D converters. For example, LaCroix does the digital bandwidth interleaving, which is something that they have invented. When I did the full teardown and analysis of their scope, we talked extensively about how that architecture works by splitting the frequency into 2 bands and then looking at TSP and combining them. Now, Keysight has their own real edge technology, which works in a somewhat similar way. It has some differences between their implementation and the LaCroix implementation. And of course, the Tektronix asynchronous time-interleaved architecture, which came a little bit later, also uses some tricks on how with DSP to correct how they sample the front end by using completely asynchronous sampling. Now, all of these techniques, they work to some extent, but they all suffer from some basic limitations. These techniques of combining signals afterwards in DSP always has the limitations of noise being overlapped, the tones being generated at the boundaries where frequencies overlap. It's a quite difficult problem and DSP intensive problem to solve this. And they work, and they have been demonstrated up to about 70 gigahertz or so from all of these companies. But what Keysight wanted to do here is to go back to really do time interleaving, basically truly do 264 gigasample per second, really, and get all the bandwidth from the front end processed by the single ASIC all the way up to 110 gigahertz. And that's exactly what they have done here. And this is a very basic representation of their instrument. It's very simple. It's just preamplifiers, samplers, and other samplers, and then buffers and ADCs, exactly how a time interleaved architecture would be like. And this time interleaved architecture is time interleaved in several layers. First is time interleaved between chipsets, and then within the chipsets is time interleaved between ADCs, and we'll talk about that in detail. But really the architecture is pretty straightforward, and this is what the architecture of pretty much every oscilloscope that relies on time interleaving architecture without doing any fancy frequency interleaving or anything like that. This is what it's going to look like. So now that we know this, let's go ahead and take a look at these blocks, a couple of these pictures here. For example, the front end is pretty interesting, the acquisition board is interesting, and I have those. And let's go and take a look and see how they're made.
And here we have all the hardware required for 256 gigasample per second of data acquisition, storage, and processing. There's a lot here to talk about, and we're lucky enough to have all the hardware to take a look at it. Now here's the main 110 gigahertz front-end sampler module. Here's the 2-channel version for the lower models. We'll talk about that as well. And of course, the entire acquisition board, ADCs, the chipset that interfaces with the ADCs, and the hypercube memory module, which is all the way at the back. And we'll take a look at these in detail. Now, what's amazing is that we are also given the ability to take a close look at the front-end module, where all the magic with 110 gigahertz of bandwidth and sampling happens. You can see here that at the back of the lid, we have RF absorbers strategically placed on top of the RFICs and some of the critical traces. And this is to be expected because everything here is in a Faraday cage. You may not be able to see through the camera, but we will be able to see when we look at it closely that these walls are all coming off the surface of the PCB, and you're creating all these cavities, and if you're not careful, you're going to create second modes in there, and it will be such a high quality factor, you will get resonances and potentially even oscillation. So they've obviously thought of that. This is what they do all the time. Now we're going to take a close look in the front end. I'm interested to see how the analog data is handled, how's the clocking handled. Clocking for A to D converters is critical. If you don't have aligned clocks for these samplers, you're going to have tones and spurs all over the place in the spectrum after the data converters. So there's a ton of engineering that's gone into this, as well as multiple technologies used to build this front end. So I'm going to take a really close look at this and analyze it, and in a way reverse engineer it to some extent. And then we'll jump into looking at the data converter and the chips that they've created for the interface, the DSP. There's a ton of stuff in here, and of course, the 2-channel version. So without keeping you waiting, let's go and take a zoomed in view of this, and I'll go over it step by step and see how it works.
So let's take a look at this front end and really analyze exactly what's going on. And there's a lot of things happening here, but we should kind of break it down step by step. I think the easiest place to start is just the front end. So the input signal enters the device from here. This is going to be a 1mm connector in the 110 gigahertz version of this instrument. Now before this connector, there is an electromechanical attenuator, and that electromechanical attenuator sits between the front panel connector and the sampler module here that you see. And the reason they put the electromechanical attenuator is because there is no way to get the massive dynamic range required from a volt per division all the way down to a millivolt per division going directly into the front end amplifier. So they divide the task of attenuation between the mechanical and the solid state attenuator or the amplifier, that's the front end. This is common, this is done all the time. However, you have to appreciate the difficulty in doing this because the loss and the frequency flatness of the mechanical attenuator, the interfaces between the connectors and the module, all of those are going to make it difficult to get 110 gigahertz bandwidth signal into this module. So they have custom designed all of these modules all made to each other. There's no cable in between, everything's assembled mechanically together. So having said that, let's assume that the 110 gigahertz signal simply enters this front-end module after the mechanical attenuator. We have a very small trace, then we have two amplifiers in a row. There's two chipsets here. These are indium phosphide front-end amplifiers and VGAs. So your solid state variable gain amplifier control and the front-end amplifier that handles 110 gigahertz of signal is all done here. The system linearity, the system noise, and the performance is determined by these front-end amplifiers. You can imagine how difficult it is to design this to have such a noise to actually get anything meaningful from the A to D converters that follow after many stages. The amount of components that are actually cascaded before you hit the A to Ds is staggering, and to be able to meet the linearity and the noise for that is really quite amazing. So having said that, these indium phosphide front-end amplifiers are designed by Keysight in their own foundry. They have their own foundry that make indium phosphide devices up to 600 or 700 gigahertz FDF max. I can't quite remember the exact numbers, but needless to say, this is a very fast process. So now signal coming out of here at this point is still a 110 gigahertz signal. Now there's also a path coming out here, all the way going into this device here. This is an edge trigger. This is a 24 gigahertz edge trigger device. It's actually not really used in this because 24 gigahertz of edge trigger is kind of a legacy architecture for being able to detect edges up to 24 gigahertz. But when you have 110 gigahertz of bandwidth, you don't really want to use the 24 gig edge trigger anymore. This entire oscilloscope uses a digital trigger. So all of that is handled by the DSP custom digital ASIC that they have designed that follows the A to D converters. We'll talk about that when we get there. But the hardware for an analog 24 gigahertz edge trigger is still present here.
The signal after that goes into our first sampler. Now here's the first really complex device that is also an indium phosphide is presented. Now this device is going to take our 110 gigahertz signal, is going to sample it with a 64 gigahertz clock in 4 phases in order to generate 4 signals coming out, each of them now having bandwidths of up to 32 gigahertz. This is how you get the reduction in required bandwidth as the stages follow on. This is again a normal architecture for time interleaved data converters. So therefore we will have 4 paths, one path over here, one path over here, one path over here, and one path over here. So we would expect these 4 paths to go into the next stages of samplers in order to be able to further break down the bandwidth so that you can actually use the A to D converter's inputs. So how do we do this 64 gigahertz 4-phase sampling? That itself is really difficult. So to understand that, we have to go from the side where the clock is now generated. Now there's an IC over here which you can barely see the edge of. This is a Hittite part. This is a 12 to 16 gigahertz, 12 to 17 gigahertz amplifier. It has a P1 dB of 26 dBm, so it can put out tons of power, which is required because they're going to divide that clock signal further down. Now it appears that the 16 gigahertz system clock comes from here, but if I understand correctly, that itself is generated from an 8 gigahertz fundamental clock, which is spread throughout the entire chassis, connecting all the different samplers and connecting all the different A to D converters to a common synthesized clock, which again is all designed by Keysight. Generating an 8 gigahertz clock clean enough to be able to feed 256 gigasample per second equivalent sampling is really challenging. Now I don't have that board unfortunately, but needless to say, it's in the 10 femtosecond range clock, which is really amazing. So now they double that apparently at some point, and then we get the 16 gigahertz clock, and there is a first power splitter here. That power splitter splits the signal into 2 parts. One side of it goes in here. Now this disappears into the board, but you can kind of roughly see where it would go. It would have to come all the way over here, and it goes underneath this module and then comes out of here and pops into this. So now you have a 16 gigahertz signal going into this chain over here. First they do some filtering to make sure there's only a single tone, and then they double it once here. So there's a times 2 over here, that's doubled. So now it's at 32 gigahertz. Once again they filter it very carefully, and then they double it again. One more time. Now we're sitting at 64 gigahertz. Now the signal is still single-ended, which means that it needs to become differential. So after some filtering, there's a hybrid here. You can see very closely. The hybrid splits the signal into 2 pieces. Now that you have 2 signals that are in 180 degree out of phase, and it appears that they put them through 2 separate amplifiers here. So they have 2 single-ended distributed amplifiers. Again, this is all in indium phosphide. Now you have a 64 gigahertz signal on one side and a 64 gigahertz signal on another side. So you get yourself a differential 64 gigahertz signal going into the front-end indium phosphide sampler. But that's of course not in 4 phases. You need to generate 4 phases from 64 gigahertz. Normally, if you're in a silicon germanium process or in a CMOS process, that's not too difficult. But in indium phosphide, you gain linearity and noise and dynamic range, but you lose complexity of integration. So making phase shifters that are adjustable in indium phosphide is quite difficult. Now I happen to know that the way they do this is that they double the 64 gigahertz yet again to 128 gigahertz, and then they process that back down in order to get the 4 phases, which is a common technique you can use if you have tons of bandwidth and tons of frequency content. You can do this in a very fast process, go in the opposite direction just so that you can create your phases. So now you have 4 phases of 64 gigahertz in here, which you can use to sample the front-end 110 gigahertz signal into 4 sections. So all of that is, again, fully Keysight design. All of these filters, every single component you see here has been custom designed to make this happen. You still need phase shifters inside the front end because you need to make sure that the alignment between the 64 gigahertz clock in 4 phases is good, and they do take care of that again inside the 3.5 process. Amazing stuff. So now you have all these 4 signals. Now you can get away from indium phosphide and make the complexity more and create signals that can be processed in a silicon germanium process. You don't need as much bandwidth anymore. The bandwidth of these signals coming out of here is no longer 110 gigahertz, is only up to 32 gigahertz. Now all these traces that you see, these are all thin film deposits. These are all again done by Keysight. This is all completely custom made.
and you can see individual cavities here. This has a depth of about a couple of millimeters. So when I put the lid on top of this, all of these are in Faraday cages, and you can see that they isolate the traces from each other, and these are high bandwidth, very low skew, good group delay paths created to make the signal as nicely preserved as much as possible before it hits the next samplers there. Now going forward, let me change the color here so that we can do the second stage with a different color. All right, let's take a look at what happens after that. Let's go back to the clock. So now the other path of the clock, the other 16 gigahertz clock, goes into this hybrid here, which then further splits the signal into 4. So now you got 1, 2, 3, 4 paths, each of them 16 gigahertz again. You can use this to feed the samplers of the stages that follow. So now following over here, we go into this. Here's another sampler, here is another sampler, going over here, here's the third one, and going over here, here's our fourth one. Now these clocks that are disappearing into the PCB, you can see the traces over there. One of them pops over here, the other one pops over here, this one, where does it go? Right there, and the last one goes all the way here and pops out of here. And if you look closely, you can see that they take the 16 gigahertz signal, and not only do they filter it, but they also passively create a 180-degree hybrid here. So there's a balun in there plus the filter, feeding the 16 gigahertz clock into the sampler here. Now this is a silicon germanium sampler. You can generate 4 phases from the 16 gigahertz in here fairly straightforward. So there's 4 phases of 16 gigahertz sampling the front end signal coming over here at a bandwidth of up to 32 gigahertz, which then creates 4 lanes, 1, 2, 3, 4 out of each of the samplers. So you can see that this splits into 4 yet again, and 4 over here one more time, and then 4 over here, 1, 2, 3, 4, and then 4 over here as the last one. So now your 110 gigahertz front end signal has now been broken into 16 differential pairs, and these 16 differential lines can now be fed into the A to D converters because now they're low enough in bandwidth. Each of them has a bandwidth of just under 8 gigahertz. Now 16 times 8 is 128 gigahertz. The bandwidth of the scope is limited to about 113. So each of these process a little bit less than 8 gigahertz of signal. But now that you have this, you can feed that directly into an A to D converter. All you need is that your A to D converter must now accept 4 lanes, each of them up to 8 gigahertz of bandwidth. Now if you do that, which means that your A to D converters would have to be each 64 gigasample per second, which is exactly what it is now. The A to D converters, one here, second A to D here, third A to D here, and fourth A to D here all have to work in parallel. So 4 times 64, you get 256 gigasample per second. But don't be fooled by the fact that you keep splitting these signals and therefore you make the job of the A to D converter easier. The isolation and the alignment and the matching between these paths is critical, because if you don't have matching between them, then you're going to get spurs in the spectrum of the A to D converters. You can't just split the signal without worrying about how much phase noise you have, how much phase alignments you have, how much amplitude balance you have. That's what the magic of this front end is to be able to take 110 gigahertz, produce a signal that can actually be processed by 64 gigasample per second A to D converters. Now just the ADC itself at 10 bits with 64 gigasample per second is itself an engineering marvel, because it's not easy to make that. But you can see that they've broken the front end a little bit differently than it is in the S-series oscilloscope, which I did a full teardown and review of before. This is the same ADC that has been upgraded and refined for this application. So you can see how they use that, and they just tweak the front end with new devices and new configurations in order to enable 256 gigasample per second sampling. Now if you look closely again, the ADC inputs from each other are fully isolated, and this reason is because it is a little bit easier to handle crosstalk within each ADC than between the ADCs. So the isolation between the lanes of these ones coming out is very important. I also want you to appreciate how difficult it must be to isolate the clock from leaking into the A to D converters, because you have 16 gigahertz clocks everywhere in multiple phases. You have multipliers and doublers which create harmonics and intermodulation products. All of these things coexist in this front-end module, all of which have to be filtered properly in order to make sure that they don't feed into the A to D converters. So really is extraordinary, and a ton of engineering has gone into making this happen. You can see custom packaging. There's devices from different technologies. Is amazing. And what is also interesting is everything is wire bonded. Yeah, they don't use flip chip technology anywhere here because you can calibrate some of those effects out, and with clever design you can get away with using wire bonds even up to 110 gigahertz, which itself is quite interesting to see. So there it is, that's the front end. So now you have an idea of what happens to the 110 gigahertz signal and how does it end up being fed into 4 ADCs at 64 gigasample per second. So now we can go ahead and take a look at the acquisition module, keeping in mind exactly what is happening here, and see how that signal is processed by the A-to-D converters. And here is the 256 gigasample per second acquisition board. It is massive and it has so many components on it, so many devices designed by Keysight. Now keep in mind there are 4 of these inside a 4-channel oscilloscope. That's because that's how you're going to get 256 gigasample per second, 110 gigahertz per channel, regardless of how the channels are configured. So it doesn't matter if you have 1 channel on or if you have 4 channels on, you have one of these dedicated per channel. And that's one of the reasons why it's $1.3 million, because you have so much independent redundant hardware to get the performance per channel totally unaffected by how much data you're collecting. So as we said, this needs to have 4 64 gigasample per second A-to-D converters in order to be able to get to 256 gig sampling, and with the 16 inputs coming from the front-end sampler I just showed you. So here's 1, 2, 3, 4 A-to-D converters, and each of these are 64 gig, 10 bits with 4 inputs. You can see some of the traces with the microstrip or strip lines that are going into it. So there's a front-end high-speed connector and an alignment pin that allows you to interface with the front-end sampler. So all the analog signals have to travel as little as possible, and they've come up with this solution with this connector. There is a front-end sample there, module there. This thing is quite heavy to lift. Oh, I'm have it the other way around, like this, and this simply plugs in to here like so. There it is, and that's 1 channel. And this then has to connect to the front panel of the instrument, so the electromechanical attenuator sits right over here, and right after that is the front end of the instrument itself. So then you stack 4 of these. So you can imagine the thermal management and the mechanical management of this itself is quite a nightmare. Now, even though you have 4 64 gig A-to-D converters here, how do you deal with the data coming out of these? Because each of these is at 64 gig 10 bit, 640 gigabit per second of data needs to be handled. Not only that, these are all working together. So you need to have the alignment, the calibration, all the coefficients to handle with the channels mismatches and channel frequency, group delay variations. All of those parameters have to be somehow handled directly from after the A-to-D converters. And more importantly, what about the trigger? This thing has a full digital trigger per channel up to 110 gigahertz, which means that you need to also be able to do that live on the data as it comes in. Of course, you can't dump that data to a CPU. There's no way, which means you have to create a custom digital signal processor chipset to handle all of that. And of course, that's what they've done. 1, 2, 3, 4. Each of these is independently connected and working together at the same time to each of the A-to-D converters. So everything you see under these 8 heat sinks, that's Keysight technology, designed and manufactured by them just so that you can package by them, just so that you can put it on this board. Now after that, you need to put the data into some kind of memory. The data is coming in at huge rates here, and the only way to handle that is you have to use a very fast memory like a hypercube. It's a 3D integrated memory. These are made by Micron. There's 4 of them again, and these actually have more than 2 gigabyte of storage, or 2 giga sample of storage. There's much more, but the scope doesn't use all of the memory, only uses a fraction of it. Because of the 32-bit architecture, you can only address 4 gig in total. So anyway, that's a minor detail and perhaps something that they will change in the future, but there is memory available more than what is spec'd for the scope. So now we have this chain. I actually have the ICs for each of them, and we should be able to take a look at it, and I'll show you that in just a second to show you what goes into those, and they're decapped, so we can even look at what's underneath them, although you're really not going to be able to see very much because it's all flip chip technology. So take a moment and appreciate what's happening here, how much technology is involved, because the front end is indium phosphide. Then we're going to get to silicon germanium, and then there is 2 chips inside the A-to-D converter, silicon germanium and then 65 nanometer CMOS. And after that, you go into a DSP, which itself is either 24 or 28 nanometer CMOS. So they've designed across so many technologies to make this happen. This is a lot of work,
And it is really amazing to see how many engineers have to work together and how complex this system is. So let's look at it a little bit from the edge here. This is a fairly thick board, as you can imagine, because these ICs have a lot of BGA balls on the back of them. I mean, look at the density of this package here. And that's the digital processor part. So then all of that, of course, has to go into the board. So I think this might be maybe a 32-layer board. Not quite sure. It's a power connector, massive, massive power connector here on the left. Some digital connectors on the other side. And check this out. This is just beautiful. A lot of linear technology DC-DC converters. These are the best pretty much you can buy in the world. You can see some of the other traces going in. There's some cable cut here. It's most likely they were injecting clock, because the clock also needs to go into these A to D converters. The clock needs to be synchronized, aligned to the clock of the front end. Oh, it's just an absolute nightmare. I'm going to zoom in a little bit so you can see some of the beautiful layout that is done here. I mean, take a look at these decoupling capacitors. It's just insane. And they're all at 45-degree angle, because you can't fit them otherwise. This thing is absolutely beautiful. I think I'm gonna have to take a couple of pictures of these and make a wallpaper out of this. It's just amazing to see how much is going on at the back of this board. So all the power handling, all the calculations for how to make sure there's no noise coupling. There is what do you do with the digital noise? What do you do with the analog noise? It's just crazy. This board design is wonderful. So now we can flip it back over here. And let's take a look at inside the package of the A to D converter. This is the same A to D converter as the S-series scope. Let me find a good angle here so we can also zoom into it a little bit more. There it is. So this A to D converter itself is a 2-chip module. There's a front-end silicon germanium module. That front-end handles the amplifying and aligning and whatever it is required to feed the signal into the 64 gigasample per second 4-channel input A to D converter, which is in 65 nanometer CMOS. It's a very straightforward packaging, nothing unusual there. You can see the front end, they have done a little bit differently in terms of where they place the balls to create good signal integrity and so on. So 2-chip solution, SiGe and CMOS, a hybrid ADC module, same thing you will find directly in the S-series scope, which looks quite nice. So then now if you're keeping track, we have a front-end indium phosphide amplifier, front-end indium phosphide sampler, SiGe sampler, SiGe preamplifier, 65 nanometer CMOS. That's how the data ultimately gets to the A to D converter. That's just crazy, crazy. And then if you can also take a look similarly to the chipset that the TSP, which is actually right on top of underneath this heatsink, you can take that cap off. That's a fairly large IC there. This is a fully digital IC which interfaces with the A to D converters. As I said, tons and tons of IOs in the back there. Very nice design, as to be expected. It looks like a regular flip chip BGA package there. All of this heatsink, of course, has to come from the top flip chip. Gives you that advantage to get the heat from the top of the IC, which is most efficient. And these are most likely some test ports here during factory testing. Maybe it's interesting to see what they're doing there around the border there. And yeah, it's a 28 nanometer, 24 nanometer, not sure, but it has all the interfaces required to grab data from the A to D and to interface with the Hypercube memory from Micron. So there it is. That's kind of what it looks like to get from a 110 gigahertz analog input all the way to 256 gigasample per second digital sampling there. Now, because this front-end module is kind of designed in such a way to accept broken down signals down to up to 8 gigahertz per channel, it means that you can take advantage of the architecture of this sampler and break it into two and make two 128 gigasample per second front end. So you can operate this half at 128 gig and this half at 128 gig and create a 2-channel oscilloscope with half the sample rate if you don't need to go to 110 gigahertz. And that's exactly what they have done, and that's what the purpose of this other sampler module is. If you look at this other sampler module, it has the same interface connector, so you can connect directly to the same front end here. And the only thing that's different is that instead of having the indium phosphide, you don't need indium phosphide anymore because the front end bandwidth can be limited to 32 gigahertz. So if you don't need to go above 32 gigahertz, well, we can give you 2 channels like this, and you can have samplers that are the same SiGe samplers, which are much simpler now to work with. And the front end can be entirely done in silicon germanium, reduces the cost significantly. The components are much fewer. Everything is flip chip over here. There's no wire bonding. This is all reflow process, makes things significantly lower cost. And now you can have 2 channels up to about 32 gigahertz of bandwidth or so, but then each of them can be 128 gigasample per second. Now this is the first time in history ever that you have a front-end module that can be configured in such a flexible way, all the way up to 256 gigasample per second. So if you buy a scope that has this in it, you can keep upgrading it by just simply changing the front-end module. By sending it to the factory, they'll just change this, but they'll keep this piece in your scope. So the same chassis with the same serial number can be upgraded across a huge range of bandwidths as your needs change, and that lowers the ownership cost of the ecosystem. That's one of the key factors here, is that you don't want to have to keep throwing everything out. And you see here's the same clocking scheme used in the back. So it's essentially identical to the other one. All you need to do is just change the front end. Back to this one, if you want to go to higher frequencies, everything stays the same, and then the software handles it. Really quite beautiful, amazing stuff going on here. The amount of engineering that Keysight engineers should really be proud to put something out here on the market. So there it is. That's a detailed look at how it works, how it compares, and how it's manufactured. But now the fun part. Let's go turn the thing on, put some signal into it, and see how it behaves.
So right now we have the scope at 500 millivolt per division, which is the maximum input signal, and this is absorbed by the front end mechanical attenuator. But we can go all the way down to 2 millivolt per division in hardware, and there's a 1 millivolt per division, which is the further amplification that's done internally. So I can go all the way down to 2 millivolt per division, and this is the best that the hardware can do. So now the mechanical attenuator is at 0 dB attenuation, and the front-end indium phosphide preamplifier is at the maximum gain. Now this is going to be the lowest noise the scope is going to be able to support. Now traditionally this noise goes up for some of the other competing products, but they've kept the noise really low, and we'll take a look at that. It's really amazing. And right now we're sitting at 1 microsecond per division over here, but check out how far you can go. It's crazy. So we can continue to go forward. Right now we are at 1 nanosecond per division, and I can keep going all the way to 1 picosecond per division. One of these horizontal divisions is 1 picosecond. That's an extraordinary thing to see, and this is what you get from 256 gigasample per second. So let's go back all the way to 1 microsecond. And the reason I want to go to 1 microsecond is because I want to capture a lot of noise and measure that noise by doing an RMS calculation directly on it. So right now the scope is set to 113 gigahertz full bandwidth and 113 gigahertz of full trigger bandwidth. So this is as much noise you can ever collect from the front end, because this is full bandwidth at play here. So let's go ahead and see how much noise that is. I've already set that up here. There it is. So the RMS noise for a 1 microsecond period at 256 gigasample per second over 113 gigahertz of bandwidth is on average about just under 700 microvolts RMS. That's wonderful. That's amazing to see. And it's at minus 50 dBm. That's the in dBm equivalent of it. This is with nothing connected to the input of the oscilloscope, as you can clearly see. Now this noise is for the full bandwidth. However, if you don't need 113 gigahertz of bandwidth, you can reduce this equivalent noise by filtering everything that you don't want. It can be all done in TSP, because the ADCs are capturing the entire bandwidth all together at the same time anyway. And there is no hardware filter in front of this. It's just not really possible to put anything in the front of this that wouldn't degrade the performance. So they just capture everything and process and deal with it in the digital DSP chipset that they have designed directly after the A to D converters. So we can go ahead and reduce the bandwidth. Let's set the bandwidth from let's say 113 gigahertz. Let's set it to 70 gigahertz. And keep an eye out on this number. Now we are sitting at 500 microvolt RMS. So you can see that the noise is gradually going to come down as you reduce the bandwidth. So if you don't need 70 gigahertz, no problem. We can try 30 gigahertz. Here you go. At 30 gigahertz, we're going to be down to about 300 microvolt RMS, which is tiny. It's by far the best there is in this kind of performance. Now, if I go all the way to 1 gigahertz, of course, you can see at 1 gigahertz, the noise almost completely disappears. We're sitting at 73 microvolt on average, or about, the mean is about 80 microvolt on average. Now, keep in mind that this 80 microvolt average noise is the noise from a front end that supports 113 gigahertz of bandwidth. If you were to build a front end only for 1 gigahertz of bandwidth, Sure, you can build at perhaps even less noise, and you can see that in the S-series scope, but this is the same front end that is capturing 113 gigahertz of bandwidth, and for that to go this low is just crazy. And it's amazing to see that the process and the design of the front-end amplifier, and of course the noise from attenuators and everything is quite good. And this is how they get some of the performances that they are able to do, and I'll show you that at the very end of the video by doing FFTs and so on, and we can see exactly how much noise can be captured. So from the noise point of view, this is amazing, and I will show you the E-knob as a function of noise as well. One of the other very interesting thing about this design is that the effective number of bits of the scope scales with the bandwidth you're using, and that's because it's purely limited by the noise, and it's not limited by harmonics and by distortion. And because if it was limited by distortion, even if you reduce the bandwidth, you wouldn't be able to get rid of it. That's a huge plus for this scope, that you can change the E-knob as a function of bandwidth, and we'll show you that plots at the end. Now, having said that, well, how do you calibrate a scope like this? You spend $1.3 million, you get a 4-channel scope on your bench, and now you want to calibrate it and align all the channels to each other and make sure that the frequency response and the group delayed response of all the channels are matched. And you would need a 110 gigahertz source, and you would need a NIST calibration in order to do this. And of course, you don't want to send the scope to Keysight every time you need to calibrate it. That wouldn't be practical. So what they have done is that they have created a probe that plugs in directly to the front, and that probe is their own design that creates a very sharp edge that allows you to calibrate the scope to the output of the probe. And I'll show you that probe in just a second, and I'll tell you how it works. It's a good, clever way of being able to do calibration directly in your lab, so you never have to send the unit back to get it NIST calibrated. And here's a close look at the calibrator. Now, the front end of the calibrator directly mates with the front connector of the unit. It's a 1mm ruggedized connector, and everything in here in this module is designed by Keysight. It has their own 3.5 process components in it, and I will show you from a photograph, and we'll talk about how it works. Now, as I said, this is a NIST calibration unit, meaning that the exact response of it up to the edge of this connector is stored in here, and once you connect this to the unit, it will download this response into the instrument, and the instrument will try and match this response from the measurements it's getting. So it doesn't even matter what that response is, as long as it has enough frequency content to meet the 110 gigahertz requirement. But that's pretty clever and a good simple way to do this, as long as you can create this device, and I'll show you what that is in just a second. And now here are some of the connectors that it comes with the unit as well. This is, for example, to convert the ruggedized 1mm connector to a V connector. There's also K connectors, and here's a 1mm to 1mm connector. And the advantage of these is that you will just basically age these connectors, and in case something breaks, it will be these ones, as opposed to the front of the unit itself. These are much cheaper to replace than, of course, the front end connector of the instrument. It will be significantly more difficult, and you have to send it into Keysight. But these also come with the UXR, the spectrum analyzer as well. So let's go ahead and connect this to the scope, but before that, let me show you what's in it and exactly how it works. And here is what is inside this calibrator probe here. So this module that we were just looking at, this is what it looks like on the inside. So there is an IC in the front, which we will take a look in just a second, and there's a signal deck which can be fed directly into this IC. Now, this signal is going to come from the auxiliary port of the oscilloscope itself, which generates a square wave. Now, the rise time of that square wave is nowhere close to 110 gigahertz equivalent bandwidth. So you're going to have to increase the edge sharpness and reduce the rise and fall times before it becomes useful for doing NIST calibration up to 110 gigahertz, which is exactly what this is. So after a little bit of filtering over here, the square wave that's coming from the auxiliary port is going to go through this indium phosphide limiting amplifier. There are multiple stages of limiting amplifier in a row here, and every time you limit this with very high gain and very high accuracy, you reduce the rise and fall times. And they do this a couple of times until it's super sharp, with the rise time only a couple of picoseconds, and then they feed that out from the connector to the scope. Now, this is really impressive. This actually means that the rise and fall times right here at the edge of the IC is even more, because without this interface and the connector and everything, because all of that is going to, of course, further limit the bandwidth. It's quite difficult to get all of that working quite nicely. So having said that, this is what's inside this, all designed by Keysight again, from scratch, just for the purposes of being able to do this NIST calibration directly on this oscilloscope itself, which is really quite impressive. So now that we know how it works internally, we can go ahead and connect it to the scope and see how it behaves. And here I have the calibrator directly connected to channel 1 of the instrument, and the interface to the front of the scope, the probe interface, is also connected, and the auxiliary output of the scope, which generates the square wave, directly goes to the calibrator. Now, as you know, as I showed you what's inside the calibrator here, those edges coming from the auxiliary are going to be continuously sharpened up until to a few picoseconds, so that we can calibrate the scope with it. And this also shows you how what kind of fast edges can actually be captured here by the scope. Right now we're looking at 512 million points, 200 microsecond per division. We can see the square wave, but we're looking at it from really, really far away. So we're going to zoom in and see how fast those edges actually are. So let's go ahead and see what happens. So I'm going to go all the way down. So right now we're at 1 microsecond, keep zooming in, 5 nanosecond, 1 nanosecond, and we're going to go here, this 10 picosecond per division. And check it out, we're looking at a 3.3 picosecond edge. That's how fast and how sharp those edges actually are, and this is why you're able to use this as a NIST calibrator. The exact group delay, frequency content, phase information that's coming out of the calibrator has been transferred to the scope, and the scope's going to calibrate itself and change the coefficients required to match that exactly. So the calibration plane of the calibrator is at the edge of the connector, and the plane of the measurement of the scope is at the connector of the scope itself, and those two are going to match perfectly, and that's how you get NIST calibration on the channel. And it looks amazing. I mean, to get a 3.2 picosecond edge measured live on an oscilloscope, it's never been done before for a real-time oscilloscope. And we can also go ahead and do a calculation and do a quick function to show what the pulse response looks like. And here's the pulse response. And you can also see even the ripple, the ringing that comes from the sharp edge, just simply because the interface is not perfect. It doesn't matter, by the way, that it's ringing, because that ring is included in the NIST calibration performance. So it doesn't matter what that it looks like. It just needs to match that response exactly. And that's the beauty of it. Each calibrator can be a little bit different, but you can still perfectly calibrate the scope as long as there is a certain performance that each calibrator meets. And you can see the ripples here. And look at this impulse response here. This is in gigavolts per second. That's how sharp this edge is. Is amazing to see this. And this is a really good way to quickly do this. And not only can you do the calibration for the phase and group delay and frequency response of the channel itself, this also aligns the channels to each other, which is another important thing, because you have a single source coming in, and that source is self-aligned to all the channels, therefore, and that's how you can get everything calibrated to each other, which looks great. So here's the setup to produce a very high frequency signal to the oscilloscope. Now I'm using an HB83752B to generate a signal up to 20 gigahertz, and then pass it to this Millitic multiplier times 6. That's going to generate signals up to 120 gigahertz, and there is a waveguide to coax converter and a 1 millimeter cable which goes to the front of the unit. I think there is something a little poetic about using such an old instrument to measure such a new instrument. There's an enormous gap in time and technology between these two units, and I wonder if the engineers who designed this ever envisioned reaching this point, which is really amazing. The other advantage of using this is that because this is such a high phase noise unit, and it has its own imperfections, and it has poor harmonic performance, we will be able to capture some of those imperfections directly with the oscilloscope and examine how the multiplier actually behaves as the input signal to it increases and how its harmonic changes. So it's going to be an interesting setup and an interesting result. So let's go ahead and zoom to the screen and see what we get. So let's take a look at the output spectrum that this instrument produces. Right now I have channel 1 set to full bandwidth, 113 gigahertz, at a full sample rate, 384,000 points and 150 nanoseconds per division. This allows me to compute the FFT, and the FFT will span anywhere from 0 hertz all the way up to 128 gigahertz at a resolution bandwidth of 1 megahertz. We can in fact look at that just to make sure the resolution bandwidth is 1 megahertz. There it is, 1 megahertz resolution bandwidth. And check the noise floor here. The displayed average noise floor for this setting is around minus 80 dBm. This is extraordinary for such a broadband front end for an oscilloscope, and there's nothing connected to the input right now. And take a look, there are almost no tones at the output of this ADC, meaning every single harmonic of every single clock that's generated is so well filtered and so well accounted for. Here there is only a little bit of a signal at 64 gigahertz in the middle of the spectrum, and that's from the front-end sampler. Very difficult to get rid of that signal, but even that is sitting at around minus 76 or 75 dBm on average. And perhaps in the future version, the final version, it might be even better than this. So having said that, this is not even at the highest sensitivity, because we are at 50 millivolts per division. If I were to reduce this all the way down to 2 millivolts per division, the displayed average noise floor at the same settings is going to continue to get better and better. For instance, I can go down to 20 millivolt per division, and you can see that the noise is already much lower, even though the resolution bandwidth is exactly the same as it was before. So if you need to make a very sensitive measurement, you can get noise floor much better than 86 dBm, simply because you can go all the way down to 2 millivolt per division, which is the limit of the hardware front-end sensitivity. Now, of course, it means that the larger signal you can capture is going to shrink as well, but if you need to make sensitive measurements, that's the way to do it. So let's go back to where we were. Because we're going to do some measurements here that's going to require a larger vertical spacing there. So there it is, back to where we were. Now I want to investigate and see what happens to this multiplier as I increase input signal power to it. Now normally multipliers have a nominal input signal under which they don't operate very well, but I'm curious to see how it behaves as I change the input signal. So right now I have it at 18 gigahertz. So 18 gigahertz times 6 is 108 gigahertz. That's what I expect the multiplier to produce. First, we're going to give it minus 10 dBm and see what happens. So let's go ahead and turn the power on to the multiplier and the signal on. There it is. Now you can see as soon as I turn the signal on, there are some additional tones appearing in the FFT. Now you don't see it at all in the vertical here because it's so small, but we can see that the instrument is capturing a signal at 72 gigahertz at minus 58 dBm. But 72 gigahertz is 18 times 4. It's not 18 times 6, which means that this multiplier right now has a larger times 4 output than it does a times 6. But even the times 6 can be seen right over here as a tiny little peak coming out at 108 gigahertz. We're not recording it because it's below the peak level that I have defined, so it's not capturing that peak there. But let's go ahead and increase the signal and see how these two harmonics interact and what happens to the input signal, to the output signal as I increase it. So here we go, going higher and higher. You can see that they're both growing, and the times 4 is still growing. We're going to continue over here. Let's stop here for a second. And right now, the two of them are almost the same amplitude. The 72 gigahertz is minus 38. The 108 gigahertz signal is minus 41. So this multiplier is still not working very well. But I expect that as I increase the input signal, eventually we're going to reach a point where the multiplier's input devices and the amplifiers, which are tuned to produce times 6, are going to operate in large signal, and they're going to get rid of the other harmonic that's undesired. So let's go ahead and try that. We're going to keep increasing it, and I expect the times 4 to begin to shrink. There it is. You can see that it's shrinking now. And I'm going to go all the way to an input signal of 0 dBm. So let's go ahead and stop at 0 dBm. There it is. And check it out. Here's our fundamental output. This is sitting at 108 gigahertz, minus 12 dBm. And the 72 gigahertz signal is at about minus 30 dBm. So that gives us 18 dB of rejection between the 4th and the 6th harmonic of the input signal, which isn't really good, but perhaps for this kind of multiplier is good enough. This also tells us that if your system is sensitive to a 72 gigahertz signal, even though this is a WR10 waveguide, if you're sensitive to this signal, you're going to have to put a waveguide filter after this. Otherwise, this is going to continue to be present in your system. And the fundamental signal sitting all the way out there is, of course, now significantly larger. And you can see a whole bunch of other harmonics here. These are all the multiples of 18, as well as all the other harmonics that this old synthesizer is producing. They're all mixing. Intermodulation products are showing up. They're just all over the place. Now, to do a meticulous test to figure out which of these is coming from what, and if any of them are coming from the A2D converters of the oscilloscope, we're going to have to do a much better source is required, and I'm going to save that for when we get the final version of the instrument. But nonetheless, we can clearly see that this instrument is going to have a very strong 4th harmonic coming out. This also means that we're going to be able to capture this in the time domain, and if I capture it in the time domain, we are going to be able to see some double edging because of all these strong harmonics present in the spectrum. We can actually test that. Let's go ahead and turn off the FFT since we're done with it. There it is. And let's go ahead and try and zoom in a little bit more. Let's keep going until we see the sinusoid. And here we go. There's our sinusoid. You can see it very clearly. This is a 108 gigahertz sinusoid, and you can see double edging and triple edging and some of this because it has strong harmonics. And look at how sharp the trigger is. And this is because the trigger has full 113 gigahertz of bandwidth done in the digital domain in the digital signal processor, and it's doing a fantastic job. And you can see how the signals spread as they move away from the trigger point because of all the other harmonics that are present. But the trigger is working perfectly fine. Now the spectrum signals that we measured, traditionally you can really only do that with a spectrum analyzer, and the only spectrum analyzer in the world that can give you the spectrum of this from DC to 110 is the UXR, which is also from Keysight. So now you can do this on their oscilloscopes as well, which is just madness to be able to do this kind of measurements up to these frequencies. It's really impressive. I also wanted to show you some preliminary measurements that Keysight has done on this instrument. And keep in mind that these are done on a prototype. This instrument is not completely finished yet, so these measurements are likely going to change and probably improve by the time the final instrument is released. Now here the instrument is set to a bandwidth of 70 gigahertz. And at this bandwidth, they're trying to measure the flatness of the front-end response as well as the effective number of bits and noise and some of the other measurements. Now, if you look here, you can see how flat the frequency response is. I mean, this is within plus or minus 0.75 dB or so, all the way to 70 gigahertz, which is the 3 dB bandwidth of the instrument. And this is not even the final version. It's very difficult to accomplish this. They also measure the ENOP. If you look at the ENOP from DC all the way up to 70 gigahertz, this dip you see here you have to ignore because that's cut off by the DSP anyway. So really the measurement that's only valid all the way from DC to 70 gigahertz, the ENOP is just below 6 dB and it's completely flat regardless of the input frequency. This means that it's entirely noise limited and it's not distortion limited. So that if you were to continue to increase to reduce the bandwidth of the front end, the ENOP is going to continue to get better and better up until a certain point where distortion might kick in. This is the kind of measurements that I would want to do on the final version of the instrument. But to be able to get this is really quite impressive. The noise we've already measured, which matches these numbers. Now we can go all the way to 110 gigahertz, or in this case 113 gigahertz. And again, you can see the front-end bandwidth here fairly flat, and this is going to further improve once they complete the instrument. Is really quite impressive. Same with the ENOP, as again flat all the way up to 113 gigahertz. Similarly, just around 5.5 dB, which I'm sure is going to be improved a little bit more too. I'm very curious what would be the ENOP, let's say at 1 gigahertz, with a 1 gigahertz filtered bandwidth and up to 1 gigahertz input frequency. But I mean, take a look at this. It's flat all the way up to 112 gigahertz, completely noise limited. This is really good, and it promises to be able to get better and better ENOP as the frequency changes. And because of this low noise performance of the oscilloscope and because of the good effective number of bits we get, we can do measurements at a performance level never accomplished before. So here's an example of a 64 gigabaud 64 QAM coherent modulation that's being used in the scope as a receiver here, and you're hitting an EVM of 2.8% for 64 gigabaud 64 QAM. That's more than 600 gigabit per second equivalent rate for coherent communication. Now the previous best measurement was at 5.4% EVM, and this improvement is primarily due to the fact that channel to channel jitter is less than 35 femtoseconds, and that means that the constellation is preserved going through the oscilloscope and ultimately digitized and processed by the DSP. Is really quite amazing. Furthermore, you can do things that could never been done before. This is a 64 gigabaud 256 QAM. That's a terabit per second equivalent coherent modulation. The EVM is again 2.6%. Nobody has ever done this measurement on an oscilloscope before. Alright, I hope you enjoyed this video. There was a lot of information in it. I definitely really enjoyed making it. I only had the scope for a couple of days, so I didn't have a lot of time to do detailed experiments with it, and I can't wait for the final full version to be out with 4 channels so we can do some crazy setup and see what we can capture with it. Now, having said that, I'd love to hear what you guys think in the comment section. Let me know what you thought of the oscilloscope, and we can discuss some of the details of its design. And if you have any questions, I'll try to answer them. I'm sure the Keysight staff would also love to answer your questions. This is a wonderful accomplishment really for engineering, and I think we should all celebrate that. I'll see you in the comment section.